So I've changed my mind about which example to give next on the, continuing this theme of abstract geometry. So this time I want to imagine picking a space that's made up of infinitely many points, 1, 2, 3, 4, out to infinity. It doesn't matter what I call my points, so I just call them these numbers. And I would like to, try to satisfy the axioms for a geometry. And so here's one way to do it. Just say that if you pick any two distinct points, the set of them makes a line. Well, that will definitely guarantee that you have at least 3 non-collinear points, and for any 2 points, they determine a unique line. So that works. That is, in fact, a geometry that satisfies the first 2 axioms. It's not the only way to go. In fact, we could instead say that the set of all even numbers, if we regard them as points, that makes up a line, the set of all odd numbers makes up a line, and then we still have to deal with the case that, what if you pick 1 and 2? Well, okay, fine, then we call that a line 2, and we also call 1 and 4, and in general, if you have any pair that has 1 even and 1 odd number, then we call that a line. And all of these lines are distinct. Well, again, you will satisfy all of the axioms of, or the first 2 axioms. So the last thing that I'll say is that, by the way, this is kind of like putting restrictions on graph theory, if you've ever heard of graph theory. If you haven't, then this may not make a lot of sense to you, but I'll just go ahead and comment quickly that graph theory is just about, you have a bunch of nodes and you have a bunch of edges. And in graph theory, these edges don't have to be straight lines. In fact, the shape of the edges doesn't make any difference, right? So any 2 graphs that have nodes and edges connected, if you change the shape of the edge, it doesn't matter. You can change the location of the nodes, and again, it doesn't matter, right? These are the same graphs as according to graph theory. So all that really matters is what's connected to what. And we can basically see certain graphs as satisfying the axioms or not satisfying the axioms. This would be one in which A and B are connected, and we take that to mean that that's a line. And B and C are connected, so that's a line. Now, we would need A and C to be connected in order to satisfy the axioms of the first 2 axioms of a geometry. So I would need to have A connected to C so that they now form a line. And now, if you pick any 2 points, you get a unique line. So that's one way to have a graph be a certain kind of geometry. Now, this graph over here would not be a geometry because you would have 2 different lines, right? It has 2 edges for the same 2 nodes, and that's not acceptable in a geometry. So you'd have to delete one, and now you almost have a geometry, except that it doesn't have enough points, and so on. And you can keep playing with these. So I encourage you, as the viewer, if you're interested in these things, to think about what kinds of variations you can do to relate, to get geometries and satisfy the axioms. Okay, on to more mundane, common sense Euclidean stuff in future videos.